I join all the previous speakers in conveying thank you to Mauro and Wilson for the invitation, for the warm welcome, and for the nice organization. What I want to share with you today, interesting data, magnetoresistance data, measured by Omri Sharon, a PhD student in my group, a work that was done together in collaboration with Avner Shaulov and Amos Sharoni at Bar Ilan and George Berger at Ortbraude. The work shows quite interesting and unexpected, at least initially unexpected, behavior of the magnetoresistance oscillations in an niobium ring as a function of the bias current that goes through the ring. And just as an abstract for the experimental work, I want to show you, thanks. I want to show you first the ring itself. The dimensions are indicated here, and the arms. I use the word arm. I adopted from a paper by Dejean, and as an experimentalist, we use the arms just to connect several more rings like that. So you can imagine now a row of several dozens of rings. This was done just to enhance, to increase the signal. But you can imagine now that the system I'm going to talk about is a ring plus two arms. And when we measure it, we saw as a function of temperature, let's say. So here is the resistance as a function of temperature, measured at various bias currents from 10 nanoamps to 10 microamps. And you see the usual behavior. You see what you expect to see, a transition around 7.2 Kelvin. And the curves, those resistance curves are shifted to the left as the bias current is increasing. So far, so good. But the surprise came when we measured the magnetoresistance. So the magnetoresistance near TC shows a very unusual behavior. At low bias current, when I say low, I mean from 10 nanoamps up to around 1 microamp, we see a parabolic behavior here, which is changing when we go to 2 microamps, 3 microamps. You see a kind of a smeared or sinusoidal behavior of the magnetoresistance oscillations. And then when we go up to 4 microamps, we see a sharp behavior here. So instead of the zero slope at zero field, you see now a very steep increase of the magnetoresistance at zero magnetic field, close to zero magnetic field. So the question is, what's going on here? And this would be the outline of my talk. I just want to discuss the physical origin of each of these oscillations, and then to discuss the effect, or to explain, or the way I understand the effect of the bias current in nanorings. So let's start with that. I start with the magnetoresistance at the low bias, and we see the parabolic behavior, which all of you know. Those are the little Parkes magnetoresistance oscillations. So let me just very briefly, very quickly explain what we see here. So what we see here is a result of fluxoid quantization in the ring. In the ring itself, the screening current is linear with the external field. So this is zero. You see here the diamagnetic linear increase of the screening current. The energy, which goes like J screening square, is of course parabolic. And this immediately explains what's going on. The kinetic energy of the current suppresses TC, or gives rise to oscillations in TC. And what we see is the following. So this is well, let's go back to here. So this is J square versus phi over phi naught. But I just rotated to show you that this immediately explains the phase diagram, the HT phase, or this line which separates the superconducting and the normal phases. So here you see clearly the oscillations in TC. And of course, immediately, this is closely related also to the magnetoresistance, which in the little Park effect is just n minus 5 over phi naught square. So that's the reason, or the physics of the, that's the physics of the magnetoresistance or the parabolic magnetoresistance in the little Parkes effect. The physics is oscillations in TC. Okay, so the physics behind the effect is oscillations in TC due to these oscillations in the screening current. So far, so good. So we understand now this curve. We want to understand now the 2 microamps and the 3 microamps, where we see kind of sinus or sinus square or whatever. In many cases, people tend to look at these sinus figures as just smearing of the little Parkes effect. Smearing because of, let's say, size variation in the rings, on whatever reason. All these smearing effects cannot explain why at low currents the effect is so nice. So what I want to suggest is a different explanation. And what I want to suggest is that in the loop, in the loop itself, we have, for some reason, which I will discuss later, we have Josephson junctions. Okay, so this is an assumption which should need to be explained later. But with this assumption, you see clearly what's going on. So with red, I refer to the normal ring, or to the conventional ring. With blue, I refer to ring with a Josephson junction. In the red, we already saw it. So the red shows that the screening is changing linearly with phi over phi naught. And as a result, the energy is parabolic. That's the red curve here. But if we include a junction in the ring, we have now a little Parkes effect for a ring for which the screening current is different. It is a sine function. And immediately you understand that if the energy is J square or I square, then delta R should look like n minus 5 over phi naught. I'm sorry, that's for the ring. For the ring with Josephson junctions, it should behave like a sinus square. So again, let me explain the essence of that. In a simple ring, the screening current is linear. As a result, the magnetoresistance is parabolic. In a ring with a junction, the story is different. We have sine behavior in the screening current, and the result sine square. With this in mind, we understand now the behavior of these 2 and 3 microamps, but the question is, are there indeed, well, it should be, are there indeed Josephson junctions, of course, in the ring? So are there junctions indeed in the ring? And even if I don't have still an answer to that, I have a strong support that this is the case, and that this support comes from the 4 microamps behavior, which, if you look at it, it resembles the behavior of a SQUID. And indeed, if you do the calculations and you look at the SQUID, and I plot here the critical current as a function, which is of course periodic with the magnetic field, with the magnetic flux, and the voltage measured in a SQUID depends clearly on the bias current. If the bias current will be somewhere here, then most of it is below the critical current, and we'll see just glitches of voltage here and there. But basically, there is no voltage at all. But if we are here, let's say at twice I critical, so if we are here, then immediately you see that the voltage is described by this function, and it's written here. So it's just sine square. It's just a sine, absolute value of sine. And let me again emphasize what's going on here. This is 0. This is 0, phi. So I see here is maximum. As a result, the resistance is minimum. But as IC is dropping quickly as a function of phi, you have here a rise in the voltage, which is described by this sign, absolute values of sine function. So we understand now the four curves. And actually, the solid lines that you see here are just, I don't want to say fits, but just taking the same equations that you saw for the little parks and for the sine behavior and for the SQUID, and adding, of course, h² term, which you need to add to any because of these arms that you have in the system. But you see, it's quite convincing that those are indeed different origins for the magnetoresistance oscillations. So here, it's delta Tc, or changing delta Tc because of changing oscillations of Tc, you have this parabolic behavior. And here, you have a different story. You have a SQUID, or effectively, you have a SQUID. You have a ring with Josephson junctions. But now, of course, comes the true question. So what is the origin of these Josephson junctions? So far, I invented them just to explain the data. But where are they from? And the answer to that starts with a work of Dejean and Alexander. They described a lasso, namely a ring with an arm, and they made calculations of the behavior of the order parameter in this particular device or particular structure, claiming that the order parameter cannot be homogeneous. It must be local dependent. And the essence of their calculations is the following. In the ring, as we increase the field, there are a lot of changes in the screening currents. The screening current is oscillating, so the energy is oscillating. So the order parameter must change along the ring in a kind of a periodic way. This arm is much less affected by the external field. So as a result, we have here a kind of a strong link, just the opposite of a weak link. So we have a strong link, which, let's ignore the details, but in the essence is that this arm forces the order parameter here to be maximum. And by symmetry arguments, it must be minimum here. So if you go this way or that way, you see changes of the order parameter along the ring. With a minimum, as I said here, at the antipodal point. But the arm, so the conclusion was that we have a special distribution of the order parameter with maximum and minimum, as I've just described. What happens if we have two arms instead of one? So just using similar arguments, what we have two maxima. We have a maximum here and a maximum there, and again by symmetry, we have a minimum here and a minimum here. So we have weak links in the ring, two weak links in the ring, due to the fact that the order parameter is local dependent in this situation. And indeed, think 30 years ago, just exactly 30 years ago, Fink suggested that for such nanoring, and nano in order to have the size of the ring comparable to the coherence length, in such a ring, you would expect that the supercurrent is that the supercurrent in the ring, the maximum supercurrent in the ring should behave like a classical SQUID. This was the idea, and indeed several works were done. Moshalkov, and then more recently Burlakov, in between them one or two more works, which studied this idea of Fink. But what I want to emphasize today is the effect of the bias current. So just before I jump to explain the role of the bias current, what I want to do is to illustrate the idea of this isotropic, a non-homogeneous local parameter, an order parameter. So you see that at, excuse me, you see that at low fields, at zero field, it's of course homogeneous, but later on, it's becoming more and more non-homogeneous. And what you see here, oops, why I cannot operate it? Okay, so let's see the movie, this video. So what you see here at exactly phi over phi naught, at exactly half of phi over phi naught, you would see at those points, you remember, this is the strong point, you have another strong point here. So at the weak points, this goes to zero, or close to zero, because of these strong points. And so this is just again as an illustration, but what I want to discuss now is what is the role of the bias current. And I think that the answer is simple, and it's nicely that it follows the Alessandro talk. I believe this is a result of phase slips in the system. Phase slips are enhanced dramatically by the current itself. So even if the order parameter doesn't go to zero at certain points, at certain fields, still the phase slips will dig in and will cause effectively a junction in the system. And this is what we actually see. We see a ring with two Josephson junctions. So that's a summary of the magnetoresistance behavior. So this is the behavior, the parabolic behavior for the little parks or low bias. We have then the sine square in between, which where the SQUID starts becoming effective, but the little parks effect still in place. And then at very high fields, at a bias current, which is twice the critical current of each of the junctions, we see an absolute value of sine. This is summarized here in the figures that you saw so many times so far. And what I want just to summarize now, the essence of the talk is the following. So we say that by switching, we can switch a superconducting ring from the little park behavior to a SQUID. By the way, we can switch it back and forth. It's a reversible process. We can switch it back and forth, but we need three ingredients or three conditions. We need the ring to be nano in order to have this condition for R comparable with Xi. We need superconducting arms, and superconducting arms just in order to, because inhomogeneous order parameter along the ring has two minima because of these superconducting arms. And I want to remind all the experimentalists here that we always have rings with arms. Otherwise, we cannot connect it to the external world. So normally, this is what we do. We take superconductor ring and connect it to the external world with two arms. And of course, we need bias current. Without bias current, we probably won't have this kind of a SQUID because the bias current enhance the phase slips in the weak points. Thank you very much.
Okay, thank you, Yossi.